Well, it's a real pleasure to be here this afternoon and to be speaking to you all and to be kicking off this conference. So over the next 20 minutes or so this afternoon, I'm going to focus on how we can start to move away from the current linear economy for plastics, the sort of take, make and waste model, towards a more circular economy for plastics, and focusing on this from a chemistry perspective. So I'm based in the School of Chemistry here at the University of Edinburgh. So we can look at any challenge, any situation as a glass that's half empty or as a glass that's half full. But when it comes to plastics, these have really been seen as a glass that's half empty in the way that they've been portrayed by the media. But I think we know that that's not the full story. Plastics play a key role in food sustainability and protecting food, which is really important in terms of a growing global population. In 2016, the transport sector became the biggest contributor to greenhouse gas emissions in the UK, and it's been estimated that this could have been doubled if we didn't have lightweight plastic components in cars and other transport vehicles. And even in things like building insulation and keeping our homes cozy, you know, this is something that, especially with the current situation, we're seeing real challenges with providing energy for this, and plastics can play a key role in this area as well. So the problem isn't necessarily plastics, but it could be the persistence of plastics in the environment. So at the moment, over 99% of plastics are made from petrochemicals, so oil and gas feedstocks. And these are typically then, from these oil and gas feedstocks, we can extract different monomers, which can then be converted into polymers that can be shaped, molded, combined with different things and used in our homes and day-to-day lives. But this article that was published in 2017 says these numbers are slightly old now, but it was really quite surprising because it showed how many plastics had been made since their concept and where these have all ended up. So what has happened to all the plastics that have been made? And over half of these have been discarded, mostly to landfill or to the environment. A small proportion have been incinerated. But if we look at actually what is currently in closed loop systems, what is recycled or is used more than once, this is a really low proportion. So the exact number depends on what source you look at, but typically it's around 10% of plastics which have been recycled. But if you look at the portion that are recycled more than once, this is much, much smaller. And so there's a real challenge here, I think, to look at how can we move away from this current setup towards something that would be more sustainable. I mean, is there such a thing as a sustainable plastic, and what would that look like? So I think to answer this question, we really need to think about plastics across their full lifespan. So starting with what are they made from? And there's real opportunities here to create plastics not from petrochemicals, but instead from renewable resources. So instead using biomass or materials derived from plants, or even carbon dioxide. I think we also need to look at how we make plastics, and I think this is actually something that's really important. While plastics are seen as being things that are quite low energy to produce, the scale of plastic production means that at the current growth rate by 2050, there would be 2.8 billion tons of CO2 produced from the plastics industry per year, and that's over twice the current aviation industry. So this would be a really significant contributor. And so I think there's real opportunities here to look to develop efficient catalytic processes to reduce the temperatures, pressures, and times of some of these reactions. And then we also need to think about what happens with materials at their end of lives. And I think this is a really interesting point because most of the materials that have been developed have been designed for really high-performing purposes, but not necessarily for their end of life. So I think it's important for us to look at opportunities to recycle plastics, and if they can't be recycled or if they were to be leaked to the natural environment, could they be degraded into non-toxic products? Or could we actually on purpose degrade them but then even upcycle them and either use them as feedstocks to make new plastics, or could we convert them into value-added chemical materials? So already this is quite a challenging combination of different things to be thinking about. But on top of this, I think we also want to have materials that could either match the properties of existing materials or that are new materials and could perform unique new functions. So It's quite a complicated situation, but also I think an area with a huge amount of potential and a lot of opportunity. So there's a real sort of desire to have things that have quite a fine balance point here, because plastics have been designed to be fit for purpose, and often this means being durable. But I think ideally we'd like to have a situation where these could also be degraded at a point of choosing, so they can be useful for their application, but then when they're finished with being used, can we at that moment trigger some degradation for these? And one opportunity, I think, here is to look at plastics that have oxygen within the structure. So many common plastics like polyethylene, polypropylene, polystyrene, these have strong carbon-carbon bonds in their structure, and that's partly what makes these materials so difficult to break down. Whereas if we introduce oxygen, which is highlighted by the red spheres here, then we can introduce breakpoints in the polymer chain. So the structure that's shown on the top right here, this is the structure of polylactic acid, which you may have come across. It's used in a variety of different plastic materials. And it's one of the most successfully commercialized bio-derived polymers. So one thing that's quite interesting about polylactic acid is that life cycle analysis has been done on this material, and this indicates that it produces less CO2 emissions than some of the conventional petrochemical plastics. So it's important to highlight that it's not a net sink for carbon dioxide. Producing materials generally produces emissions, but this can be reduced by using polylactic acid. But I think something that's really key with this is that it can get us to think about this almost as a concept piece, because it can get us to think about the assembly and disassembly of different polymer materials and how we can reversibly make and break these bonds in the chemical structure to degrade materials down into small molecules. So this slide shows a chart which is taken from a recent report from the Royal Society of Chemistry on science to enable sustainable plastics. And what this chart shows is different plastics that are either biodegraded and or biodegradable. So it doesn't include examples that are petrochemical based and are not degradable. But there's a few things that I want to highlight here. One is that just because some material is bioderived, it doesn't necessarily mean that it is biodegradable. And on the right-hand side, so the examples shown in yellow and blue are both biodegradable. But one of the key things that I want to highlight here is that all of these examples contain oxygen within the structure. So I think there's a real opportunity here to look at polymer materials that contain oxygen within that structure as a potential to enhance the degradation of these materials. So in our lab, we've been looking at multiple areas of this, but one thing we've looked at is how we can take polylactic acid, but change the material properties of this. So polylactic acid, while it has many useful applications, these can sometimes be limited because of the material properties. And one opportunity to modify these material properties is to combine polylactic acid with a different monomer to make a block copolymer. So in our laboratory, we've looked at combining this with caprolactone, which is quite a flexible monomer. You can see there's quite a long chain in the structure here. And so the flexibility of this component can help to reduce the brittleness of these materials. We've also looked at combining this with other cyclic esters, so such as beta-butyrolactone, to form other block copolyesters. And one thing that we were really quite excited about is that we can combine these two materials to make this block copolymer, where there's 3 different sections of that polymer chain with the different monomers. And to the best of our knowledge, this was the first time that this polymer structure had been reported in literature. And this is something that we're quite excited about, because in all of these different blocks of the polymers, we have these potential degradation points. So just a few things that I'd like to highlight are that the formation of block copolymers, I've mentioned that these can be used as a strategy to diversify the material properties available. But with this particular example in the top right, our catalyst, which is shown just here, produced this block copolymer in 7 minutes. And from when we did a literature search, it seems like this is really quite active, as most of the other literature examples, or well, all the ones we found, took sort of between 1 and 96 hours. So our catalysts seem to be quite fast and quite efficient for this polymerization. We've also been able to maintain the control, or actually slightly improve the control. So this value shown here is the dispersity, and this is the distribution of the polymer chain. So whether we have, if we have a dispersity value of close to 1, it means that all those chains are very similar length. Whereas if we have higher values further away from 1, it means that we have some short chains, some long chains. So even though our catalyst was very fast, then it actually still gave very good control over the polymer structure. So there are other opportunities to produce a range of different polyesters and other oxygenated polymer materials. So some other examples of these are to combine epoxides and anhydrides to make polyesters. And this is something that I think is an interesting approach, because we have different sites of functionalization on the epoxide and the anhydride unit. So unlike some of the, like the structure of polylactic acid, we have multiple points here where we can change these different functional groups to give polyesters with different material properties. And there's opportunities to derive both of these monomers from bio-derived sources. So some examples shown here include limonene oxide and succinic anhydride. And limonene oxide, I think, is a particularly interesting example, because this is something that is present in the peels of citrus fruits. So there's a huge amount of waste from the juicing industry. So there's opportunities with this type of technology to create polymers from materials that would otherwise be waste. Instead of using the epoxide and the anhydride, there's also opportunities to replace that with carbon dioxide. And this, I think, is a really interesting strategy, because it produces polycarbonates from CO2, so something that's a waste product from industrial sources, that's cheap and it's abundant. And these polycarbonates have quite different material properties to what we know as conventional polycarbonates. So the way that you'd maybe have interacted with polycarbonates would be sort of mobile phone protective cases. It's usually quite a tough plastic, whereas that's not necessarily true for these polycarbonates. So it's not that these are a direct drop-in replacement. But where they're really interesting is if they're reacted with another small molecule called a diisocyanate to produce polyurethanes. And these components of the polyurethane being made from partially carbon dioxide can give polyurethanes with similar material properties to those formed through conventional routes. So polyurethanes are again used in a range of different properties or different materials. They're used as the soles of high-performance running shoes. They're used as protective coatings on cars and white goods. And they're also used in foam. So actually the seats that we're sitting on today probably have a polyurethane foam held within them. So life cycle analysis has also been done on this polymerization, and it indicates that by having 20% of the final structure from carbon dioxide, there could be up to 19% greenhouse gas reduction associated with making these materials. And something that's emerged from literature recently is that there's opportunities to use flue gas from power stations as the source of carbon dioxide. So there was an experiment done where this gas was collected, put inside what was essentially a glorified plastic bag, and then a pile of textbooks put on it to force that gas through into a reaction setup. And some catalysts can now tolerate the use of this carbon dioxide to make polycarbonate materials. So in the next few minutes, what I'd like to cover is looking at some examples of efficient catalysis to make a range of these different materials. So in our lab, one thing that we're particularly interested on is the use of two different metals, and can we combine these to access catalysts that deliver the best of both of what each of these metals can do individually. So catalysts based on potassium, and this is for the synthesis of polylactic acid, generally give really high catalytic activities, but they generally give really poor control over the polymer properties. Whereas in contrast, if we take zinc, then we can access materials with good polymerization control, but some of these are slower to react than the potassium systems. So what we look to do is to see whether we could combine both of these metals within molecular structure to access this overlapping point where we could highlight access the high activity and also the good control. And we were able to do this. So this is a simulation of one of the molecules that we designed as a catalyst. So you can see there's a potassium metal center here, and there are 2 zinc centers here in this molecule. And we found that this catalyst really could deliver the best of both. So we see that it accesses activities as high as the potassium systems, but the control is in line with that of the zinc catalyst. So I think there's real opportunities here for mixed metal catalysts to deliver improved performances. This concept has also been something that we've looked at with anhydrides and epoxides to make polyesters. And so the structure that's shown on the right here, you can see there's 1 zinc center and 1 magnesium. And when we look at the activity of this system for polyesters, then this catalyst is about 40 times faster than the mixture of the homometallic systems. So what I mean by that is that if we take one catalyst where there's 2 zinc and 1 with 2 magnesium, and we combine those in a 1-to-1 ratio, then the mixed metal catalyst, which has the 2 different metals in one structure, is 40 times faster than that. So we can access really enhanced activities by having these mixed metal systems. Okay, so in the final few minutes, I just want to touch on what opportunities there are for plastics at their end of life. And I think this is something that is going to be really key because, as I mentioned in one of the earlier slides, out of all the plastics produced every year, it's really a tiny fraction that is in closed loop recycling. So this is 2% that's in closed loop recycling at the moment. And I think there's a lot of different ways to keep plastics in this circular loop. One of the key things is what they are made from. So can we, for example, if we use things like polylactic acid, can we have materials that are made from plants that can be composted and then used to generate new plants? Is there opportunities as well to product reuse, and so to reduce the amount of materials that we're using and we're interacting with? But I would think other areas where chemistry has a really key role to play are in mechanical recycling and chemical recycling. So with mechanical recycling, one of the challenges associated with this is that every time you mechanically recycle, so you reshape mixtures of plastics, then there's a reduction in the properties of that material. And one of the reasons for this is because if you have 2 different plastics, they behave like oil and water. So there's an interface between them. And if you put any sort of force in that material, then this can cause a lack of adhesion at that interface, which can introduce weak points into the material. So one area of research that's been emerging in this field quite recently is the opportunity to use molecules that can act as zips or almost like staples across the interfaces of those different plastics to link them together so that if a strain is put onto those materials, that they can still have good interactions at those surfaces and deliver improved properties. I think there's also really exciting opportunities in terms of chemical recycling. So this is the concept that I was describing with polylactic acid. So if we almost think of it as a tower of Lego blocks, it means that you could deconstruct and then reconstruct that tower of Lego blocks so that you can access a final product that has exactly the same material properties every time, rather than seeing that reduction in properties that can be associated with some mechanical recycling processes. And if this isn't possible, then can we at least recover energy and keep the carbon in a closed loop system? So, oh yes, this is just to show the concept of using these molecules as chemical zips. Okay. So just to conclude then, what do we need for the future? Well, I've just put a few things on the slide. I think there's a really extensive list of things that are potential opportunities in this field. But I think there's opportunities around substitution. So can we use alternative materials that might deliver either improved properties or more sustainable options than some of the existing materials? I think within this, there's also opportunities if we can develop plastics that have improved properties, do we actually need less of them? I think there's a real potential for oxygenated polymer materials. So some of the examples that I've shown throughout the talk are polyesters and polycarbonates, but there are other classes as well, such as polyacetals and polyethers. In terms of the efficient processes, I think there's really key opportunities for catalysis, and something that I've not really touched on today is alternative processing methods. But I think underpinning this, there's also the really key consideration of energy, and where are the energy sources for these different processes. If we have opportunities to use renewable sources. And then I think at the end of life, there's a huge amount of interest, for me certainly, in terms of materials recycling and how can we keep things in closed loop systems, and also looking at conversion technologies. So something that Stephen Wallace will be covering in the talk later is how can we take plastics as feedstocks and convert them into value-added materials. So with that, I would just like to finish by thanking my team. So some of the work that I touched on briefly today has been performed by Veronica, by Anna, and then others from the team. I'd also like to thank the funding sources for making this work possible. And finally, thank you very much for your attention. Thank you.